This video will be the first in a series covering thermodynamics, and this will be covering it at the level of about a 300 or 400 level undergraduate class. What I'm going to do in this video is go through just a few quick definitions of some things that you will probably want to know before watching these videos. So these would be things that are studied in an undergraduate general chemistry level class. The first thing is thermodynamics here. So broadly speaking, this is the study of the relations between energy, work, heat, and temperature. So we say up here that it's the study of energy, work, heat, and temperature. So now we want to be able to know what each of these terms means. So energy is the capacity to do work or produce heat. Is often denoted as uppercase E, and it has units of joules. And this can be broken up into kinetic energy, so that's the energy of motion, which can be denoted as KE or KE or E sub K or K, or in classical mechanics T. And it has this equation where it's the kinetic energy is equal to 1/2 times mv squared, where m is the mass and v is the velocity. Then the potential energy, which is the energy possessed due to some position in a force field. So this can often be thought of as the stored energy that could become kinetic energy if it were allowed to start moving, for instance. This is often denoted as this PE, or the PE without the periods in it, or U or V. And so now we see that we've defined energy as the capacity to do work or to produce heat. So we want to know what those two things are. So work is just the exchange of energy which results in externally measurable macroscopic forces on the system's surroundings, which can cause mechanical work to, for example, lift a weight or cause changes in electromagnetic or gravitational variables, which is just a fancy way of saying something like lifting something up. This is often denoted with capital W, sometimes lowercase w, or in the differential form. So I'm using the delta here because, as we'll see in later videos, work is not what's called a state function, so we would not want to use a proper differential for it, since the path that you actually take to gain or use work is going to actually matter. So it's not a state function. And this will have units of joules. So broadly speaking, we can think of work as the energy that can be put to use, which is why we call it work, because it's energy that can do jobs, it can do work that we are actually interested in. Then heat is thermal energy in the form of random, usually at least close to isotropic. Obviously we can have a flow or a movement of heat, so it's not always isotropic, but when we think of heat, we tend to think of it as just particles moving in random directions, such that the particles are not moving anymore in any particular direction compared to the others. And so this is going to be based on the kinetic energy, and is transferred from a hotter system to a cooler system that are in contact. Heat is often denoted with Q, that can be either lowercase or uppercase, or as we'll talk about in later videos, it can be equated to the enthalpy, which is going to be what the internal energy is when we're at constant pressure and volume. So broadly speaking, and somewhat inaccurately, heat is energy that cannot be put to use. We'll see, for instance, in like the Carnot cycle, that heat can be put to use for doing work, but generally the breakup of energy between work and heat says that work is energy that can be used to do things that we're interested in. Heat is just kind of a wasteful byproduct. Then the temperature, which, remember, when we're in thermodynamics, we do not want to equivocate between temperature and heat, because heat is actually the energy, where temperature is the average kinetic energy of the system. So what that ends up meaning is that heat is going to be an extensive property and temperature is an intensive property, meaning that if you have two systems with an equal amount of stuff at the same temperature, if you combine them together, you will actually double the amount of heat in it, but the temperature will not change. Temperature is often denoted with a capital T, and it has units of Kelvin. We know that it also can have units of Celsius and Fahrenheit, but in thermodynamics, we are pretty much always going to be using the Kelvin scale for the temperature. Then we also want to think about what's called the system and the surroundings. So a system is the artificial demarcation of energy or matter into that which is under study. So the system is the thing we're interested in. Variables are shown from the system's quote-unquote point of view, such as the loss of heat from the system. And so if the system is losing heat, then it will be negative heat because the system is the thing that has lost the heat. Or if the system is doing work on something else, then that is also going to be negative, since that is essentially energy that is going from the system into whatever it is doing work on. Then the surroundings is pretty much just everything else that is not in the system. If the system is losing energy, then it will have a negative sign, and so then the energy has to get lost. It's going to get lost into the surroundings, and so the surroundings must be gaining the heat. So it's going to have the opposite sign, where if the system is losing heat, it's negative. That means the surroundings are gaining heat, so it's positive. And we can have multiple different types of systems. And this is always important to remember, because in a lot of thermodynamics, people will toss around this is an isolated system or a closed system. And it's always important to remember that there is a very precise definition for these things. So an isolated system is one that does not exchange neither energy nor matter with the surroundings, where a closed system is one that can exchange energy but not matter. Then an open system is one that can exchange both energy and matter with the surroundings. The next item on our list here is what's called the internal energy. So this is the total kinetic energy due to the motion of particles. That can be things like translational motion, rotational motion, and vibrational motion. And the potential energy associated with the vibrational motion and electric energy of atoms within molecules, often denoted with a U, E, or for changes, it can be delta U and delta E, and it has the equation, so the internal energy is equal to the kinetic energy of the system plus the potential energy of the system. And we can see that the change in the internal energy is equal to the heat plus the work. And what you'll notice here, I'm going to be using E for the internal energy instead of U, even though U is quite often the more common one, especially if you've taken general chemistry. They have probably almost certainly used U. But the reason for this is because we're going to be using U for various potentials, and the textbooks I'm using for this both use E for the internal energy. And so I will be using the E for the internal energy here. Then we can also have what are called exothermic and endothermic processes. So in an exothermic process, heat flows from the system to the surroundings. The heat of the system will have a negative sign since it is losing heat. The surroundings will therefore feel warmer since they are gaining heat. So that looks like this over here, where we can see the system is losing heat into the surroundings. And so the Q here, which as we'll see in future videos, in most instances can be equated to the delta H, so the change in the enthalpy here, that will be less than 0. So remember, this is from the system's point of view. The system is losing energy, so the Q is going to be negative here. Then we can have endothermic, so heat flows from the surroundings to the system. The heat of the system will have a positive sign since the system is gaining heat. The surroundings will therefore feel colder since they are the things losing heat. So that's what's shown on the right side here. So we have heat coming from the surroundings going into the system. So we can see the surroundings are losing energy. That's why the surroundings will feel colder. And then the next item on the list here is something that I've already mentioned. It's a state function. So this is a function in which we are concerned with the difference of the state at two different times, both at equilibrium, rather than these state values or how we got from one state to another. So it's essentially saying we don't care how we got from A to B. All we care is what is the difference between A and B. And again, this is both states at equilibrium. A couple of the state functions that we're going to be looking at are the entropy, which loosely speaking is the highest probability states of a system. We will define this a lot more rigorously as we go. We'll be spending quite a bit of time discussing entropy and what entropy actually means. This is often denoted with the S, or for a change, the delta S, and has units of joules per Kelvin, or sometimes joules per Kelvin per mole. Then we can have enthalpy, which we've already mentioned before, is often just equated to the heat, since the heat at constant pressure is usually what we're doing in like a laboratory setting. So loosely speaking, it is the heat at standard temperature and pressure. Again, we will come to a more rigorous definition as we go, especially when we're talking about the first law of thermodynamics. This is often denoted H, or for a change in entropy delta H, and has units of joules or kilojoules, or it can be joules per mole or kilojoules per mole. And this is defined as the sum of the internal energy E plus the product of pressure and volume. So like I said, if we are looking at processes that have a constant pressure and volume, then we can often just ignore that, and then we can just equate this with the heat. So at standard temperature and pressure, it is just that the enthalpy is equal to the internal energy here. Then another state function that will be of interest to us is what's called the Gibbs free energy. This is used to calculate the maximum amount of work, other than pressure volume work, that may be performed by a thermodynamically closed system at constant temperature and pressure. So this is often denoted as G, or for a change it's delta G, and has units of joules or kilojoules, or it can be joules per mole or kilojoules per mole. And this can be calculated using these two equations. The next item on the list here is what's called the activation energy. So the activation energy is just the energy needed to initiate a reaction. It is the energy needed to either break bonds in a molecule and or overcome the repulsive forces between two particles. And it is denoted as E sub A. And for either type of reaction, all it is just the difference in the energy between either the reactants in the transition state, if it's an exothermic reaction, or the products in the transition state, if it is an endothermic reaction. Because we see that the heat that is different between the reactants and products, when not considering this transition state, is either just the heat of the reaction, which is given off in an exothermic reaction, or the heat of the reaction, which is absorbed in an endothermic reaction. The next thing we want to look at is what's called the spontaneity, or spontaneous. So a spontaneous process is a process that will occur on its own without any external work. So this does not say how fast a process will occur, only whether the process is thermodynamically favorable. And this will be a process that has a negative delta G. Then kinetics, which is more what we were looking at up here with the activation energy, is the rate at which the process will occur. So remember, whether something is spontaneous or not tells us nothing about how fast it will occur. For that, we have to look at the kinetics. Remember, kinetics is ultimately determined by the thermodynamics, but in chemistry, we make a distinction between the thermodynamics, which is whether a process is favorable or not, and the kinetics, which is how fast the process will occur. So if we think of a generic reaction like this one, where you have A plus B becoming C plus D, then the rate law for this, we can see this only takes into consideration the concentrations of the reactants, not the products. And then this K sub R here, which is just our rate constant, is going to be calculated using this Arrhenius equation here, which we can see is going to be based on the activation energy and the temperature. Then this A sub naught here, which I just put the sub naught there in order to distinguish it from the A in here. So it's not the same thing there. So this is just the pre-exponential factor, which essentially tells us how often particles run into each other with the correct orientation to actually react. Then we see, getting back to thermodynamics, we also have equilibrium. This is also extremely important, and we'll be spending a lot of videos later on in the series talking about equilibrium. So at the general chemistry level, what you should know about equilibrium is that equilibrium means that no net macroscopic flows of matter nor of energy occur within a system or between systems. So in a system that is in its own state of internal equilibrium, no macroscopic changes occur. For instance, we can have some function here of the energy, volume, and amount of stuff at time t1 will be equal to that same function on this energy, volume, and amount of stuff here at t2, so at some later time. And this is for any macroscopic function f. In chemistry, for the generic reaction of A plus B becoming C plus D, we want to find the equilibrium expression for this constant, which again is just the product of the products over the product of the reactants. So that would look like this for our generic reaction. And when a reaction is not at equilibrium, instead of Kc, we use what's called a reaction quotient, or Qc, instead of the equilibrium constant Kc. If Qc is greater than Kc, the reaction will proceed towards the reactants, because now we can see that we are top heavy in this ratio of products to reactants here. If the Qc is smaller than Kc, then the reaction will move towards products. If it's equal to Kc, then we're at equilibrium, and we do not get any net change in the concentrations of products or reactants. And so for energy, when we're at equilibrium during some time interval here from T1 to T2, we say that the delta H, so the change in enthalpy of the system, is 0, the change in entropy of the system is 0, and the change in the Gibbs free energy of the system is also 0. So again, equilibrium means that there's no net change in the matter or in the energy of our system. So those were some important definitions for us to know. Another thing that you might know about thermodynamics is that it has these laws of thermodynamics. We'll go through these in a very quick overview here. So it's called the zeroth law of thermodynamics. Some people consider this not really a law of thermodynamics, which is why it's kind of wedged in here as the zeroth law. But this says that if two closed systems, so remember closed means that we are not exchanging matter, only energy. So if two closed systems are in thermodynamic equilibrium with a third closed system, then the two original systems are in thermal equilibrium with each other. Basically, if we have some system A, which is shown in this blue one right here, which is in thermal equilibrium with C, and system B is also in thermal equilibrium with system C, then systems A and B are in thermal equilibrium with each other. So we can think about it like this. If we have some cold system here, some hot system here, and some room temperature system here, such that all three of these systems are closed and they are not equal in temperature with each other. We bring them together so that they can actually exchange energy with each other, but remember, not matter. This is a closed system. They will end up becoming equal in temperature, and that's when they will be at thermodynamic equilibrium with each other. So that is the zeroth law. The first law of thermodynamics says energy can be converted from one form to another with the interaction of heat, work, and internal energy, but it cannot be created nor destroyed. This means that any energy, heat, or work coming into our system must be coming out from the surroundings. And likewise, any energy, heat, or work leaving our system must be going out into the surroundings. This is summed up in this relationship here. So we have some differential change in the energy of the system that's going to be equal to some differential change in the heat or the work, and this is equal to the negative differential of the energy in the surroundings. So this negative here is telling us that if we have energy going into the system, it must be coming from the surroundings, or similarly, if we have energy going out of the system, it must be going into the surroundings. So for instance, in this example above, if we say that we have this that's colder than this, but this is colder than this, we put them together, they will exchange heat until they come out to the same temperature as each other. And more generally, because of the energy and mass equivalence, E equals mc squared, this can actually be generalized more into what's called the conservation of mass energy. Then the second law of thermodynamics says that the state of entropy, which we haven't really defined very well yet, but like I said, we'll spend quite a few videos defining and talking about what entropy is. But we can say that the state of entropy of the entire universe as an isolated system will always increase over time. The second law also states that the change in entropy in the universe can never be negative. So if we have some differential change in energy of the universe, this would be equal to some differential change in the entropy of the system plus the differential change in the entropy of the surroundings. This has to be greater than or equal to 0. And a corollary to the second law of thermodynamics is that in an isolated system, natural processes are spontaneous when they lead to an increase in overall entropy. Then we have the third law of thermodynamics, which tends not to be as important as the first and second, and so we're not really going to talk about it as much in this series of videos, and we won't be talking about it until quite a bit later. But what the third law says is that the entropy of a perfect crystal is 0 when the temperature of the crystal is equal to absolute 0. We can see this, for instance, if we look at this equation here, which tells us that what the entropy is, where the entropy is equal to the Boltzmann constant, which is just a conversion between energy and temperature, multiplied by the natural log of the number of microstates. We can see at 0 Kelvin, we only have one possible microstate. So if we take the natural log of 1, that equals 0. So we can see that a perfect crystal at absolute 0 will have 0 entropy. And one last thing I wanted to talk about in this video, which is just the broad and tentative outline for these videos. So in the next couple of videos, we're going to be doing a quick overview of gases and the ideal gas law. Then we'll go into several videos about the first law of thermodynamics. Then we'll go into quite a few videos about the second law of thermodynamics. Then we'll talk about what are some potentials and properties in thermodynamic systems. Then we'll look back again at gases, but now using some of these things we learned in parts 2, 3, and 4. Then we'll look at phase equilibrium. So this is the equilibrium between different phases of matter. Then we'll look at chemical equilibrium. Then we'll do our brief look at the third law of thermodynamics. Then we'll look at some basic statistical mechanics. So this will not be a replacement for a full semester class of stat mech, but we will look at some basic statistical mechanics. Then we'll look at reaction equilibrium and reaction rates. Then we'll look a little bit at some electrochemistry. So this is extremely tentative here, but this is about the percents that I will be spending on each of these topics. And these references right here, these two textbooks, are the ones that will be used throughout. Any other sources I use will get cited throughout, but you can assume that these two sources right here are used in pretty much every one of these videos. But I'm kind of bringing both of these things together and combining them into one full curriculum. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.